Okay, let's begin. So I'll speak about reconstruction of small molecular structures. And okay, so let's start. There is a common belief in the cryo community that we cannot use cryo-EM to reconstruct very small structures. And the reason is the SNR. So small molecules induce low SNR. So here you can see 3 examples. So in the left panel, you see a data set, a micrograph of a big protein. So basically, it's very easy to see the projection images. So you can imagine it's quite easy to extract them, and then to get a stack of images, and then to recover the structure using standard algorithms. So this seems like a very easy data set. In the middle panel, you see a data set of a smaller molecule. Here, the molecular weight is around 465 kilodalton. So the SNR is lower. It's harder to see the projections, but we can still see them. I think this is one, and perhaps here. So this still seems to be okay. Here you can see a data set of a much smaller molecule. So here the weight is only 82 kilodalton, and basically, where is it? Oh, here, basically I don't see anything. But somehow they managed to take this data set and actually to recover the 3D structure, which is quite impressive. I have no idea how they did it. But you can imagine that as the weight, the size of the molecule gets smaller, the SNR drops even more, and basically you won't see anything in the data. So this is standard reasoning. So small molecules, they induce low SNR, therefore we cannot detect the particle projection, so particle picking fails, and therefore we cannot reconstruct the 3D structure. So there are several examples for such arguments. I think that the most celebrated one is the paper of Richard Henderson that was mentioned yesterday, where basically Henderson calculates the smallest molecule that we can recover, and his number is around 40 kilodalton. The specific number is not very important for this talk. And more precisely, Henderson calculates the smallest molecule for which we can recover the pose parameters, the 2D location, the 3D orientation. In his Nobel Prize lecture, Joachim Frank provides a similar argument. The specific argument is a bit different, but it's the same story. So he has a different formula, but again, he says that you cannot recover the molecule below some threshold. And the key observation, and this is the key for this talk, is that there is a gap in these arguments. And the gap is that they always assume, either explicitly or implicitly, that you must determine or estimate the pose parameters in order to recover the 3D structure. But if this is not true, if you can recover the structure without estimating the pose parameters, without estimating the rotation and especially the locations, then the impossibility of, for example, detection does not necessarily imply impossibility of reconstruction. And therefore, perhaps we can recover structures in very low SNR environments. And therefore, again, perhaps we can recover very small structures using cryo-EM. So let me try to illustrate it. So the purple boxes are what we do today. So basically, we take the data set, the micrographs, and then we perform particle picking. So basically, we locate and extract the particle projections. We get a stack of images, and then we use this stack of images in order to recover the 3D structure, for example, using expectation maximization. If we can go directly from the micrograph to the structure, which is what I try to suggest today, then basically the problems of particle, again, the impossibility of particle picking does not translate into impossibility of reconstruction, and we may be able to recover the structure in very low environments. Okay, so let's think about this problem from an estimation theory perspective. So suppose we have a 3D structure which is described by n parameters. And we collect n particle projections. This is data that we collect. So each particle is associated with 5 parameters, 2 parameters for its location in the micrograph and 3 parameters for the rotation. So overall, we have L plus 5 n parameters that we don't know. If we want to estimate the structure and the parameters, like people did in other cryo-EM algorithms, then the number of parameters that we want to estimate increases linearly with the number of projections. So as we collect more and more data, we also need to estimate more and more parameters. And in this case, like classical estimation theory, tells us that it's not clear that we can actually formulate a consistent estimator. Consistent estimator is an estimator that as we gather more and more, as we collect more and more observations, the estimator will converge to the ground truth, to the parameter of interest. So in this case, it's not clear that we can do that anymore. And there are several examples. So I think that the most famous one is called the Neyman-Scott paradox. I think it's from the 60s, which is a very nice, simple example where they show that maximum likelihood is not consistent. And another example, which is more relevant to cryo-EM, is the problem called multi-image alignment, where basically you get many copies of an image, and each copy is a bit shifted, and you want to estimate the shifts. So again, the number of parameters increases with the number of observations, and it was shown that the Cramér bound of this problem is independent of the number of observations and is proportional to the variance of the noise. So again, we cannot estimate the parameters consistently. Okay, so what can we do in this case? So we can marginalize over the nuisance parameters. So nuisance parameters are the parameters that we don't know, but the goal of the task is not estimating them. So in cryo-EM, these are going to be the locations and the rotations of the particle images. So what we actually care in cryo-EM is only to recover the structure. So we can treat the rest of the parameters as nuisance parameters. And if we marginalize over them or average out these nuisance parameters, then we only estimate the parameters that describe the structure. And this is a fixed number of parameters. So in this case, we can, if we have enough data, we can collect more and more data, but the number of parameters remains fixed. And therefore, perhaps we can come up with consistent estimators. For example, maximum likelihood is going to be consistent. And now that the current situation in cryo-EM is a bit strange from an estimation theory perspective, because it's in hybrid situation. Because we do particle picking, so we're trying to recover the locations of all particles. So these are two end parameters. But in the reconstruction or the refinement stage, we usually marginalize over the parameters using expectation maximization. So overall, we have two end parcel parameters that we want to estimate. So again, this increases linearly with the number of observations. And therefore, it's not clear that the estimator is consistent. And specifically, we know that if the SNR is very low, we cannot detect the particle projections, therefore, basically, it fails. And the algorithm is not, the estimator is not consistent. So today I suggest two methods to marginalize over all the nuisance parameters, the rotations and translations. Okay, and try to come up with consistent estimator to recovery, especially in very low SNR environments. So before I introduce the methods, I want to introduce a simplified model of cryo-EM, a toy model. It will help me to explain, or for you to understand the principles of the method. So first of all, I'll explain the methods for this simplified model, and then we see how we can use the same principles all the way to cryo. So this simplified model is called multi-target detection. So in this case, the measurement is just one-dimensional, very long measurement. And the measurement contains multiple occurrences of a signal, x. And the goal is to estimate x from the measurement. Okay, and we treat the locations of the signal occurrences, we treat them as nuisance variables. So we don't know them a priori, but the goal of the task is not estimating them. So on the left panel, you see an example in the absence of noise. So basically, we have one-dimensional measurement. Here, it contains like 100 elements. And you can see three signal occurrences. This one, this one, this one. In the middle panel, you see the same problem in the highest SNR regime. So you can still see the signal occurrences. And you can imagine that it's quite easy to detect the signal occurrences, extract them, and average out the noise. So this is somehow similar to what we do in cryo-EM nowadays, that we first pick the particles and then try to recover them. Here you see the problem in the low SNR regime. So the noise is the SNR is very low. We don't see the signal occurrences anymore. And again, you can imagine it's quite difficult to detect the signal occurrences in this situation. And again, if the SNR drops even more, at some point it becomes impossible. You can prove that it is impossible. And the question is whether we can still estimate the signal in this situation where the SNR is very low and we cannot detect the signal occurrences. And if you can do that, how? Like what algorithms can you use? Okay, specifically I discussed today two methods. Autocorrelation analysis and approximate expectation maximization. Any questions? Yeah.
what actually defines, why does a smaller protein have less signal to noise? Like is there a limit that prevents us from zooming in more? Of course, as we zoom in more, as we magnify more, we can have less of a field of view, so we have to collect more data. But is there something fundamental with like a diffusion scale and the size of the protein that...
So first of all, I'm sure there are better experts than I do in this room, much better experts than I am, but basically the electrons, they convey less information. That's the main problem. It's not about the zoom or the scale or anything like this. You just get less information, less contrast. I think this is how I understand it, but again, there are much better experts about the physics of the problem than I am.
There's less atoms to scatter off of, so there's less electrons that get scattered.
Okay, that's more or less what I said, right?
Yeah.
Thank you. No, but yeah, so that's the fundamental problem of the physics of the problem. And below a certain threshold, the point here is that below a certain threshold, you actually cannot detect the particle projection in the data, no matter what you're going to do. And the question is whether you can still recover the structure or you cannot detect the particle projection in the micrograph. Okay. Now, okay. So I'll start with autocorrelation analysis, the first method. First of all, remind you what is autocorrelation analysis, and then we see how we can apply it to multi-target detection, the simplified model, and then how we can use the same principles to cryo-EM. So autocorrelation analysis, it's an estimation method. So we have a signal y, which in our case, this is the measurement. And it's a random signal whose distribution is parameterized by x. In our case, this is going to be the signal of interest that we want to estimate. And the goal is to estimate x from y. So we have 3 stages. In the first stage, we compute or derive the expected autocorrelations. So this is something we can compute from the statistical model. And these are going to be functions of x, of the parameters of interest. Specifically here, I wrote down the first 3 autocorrelations. So in our case, these are going to be polynomial functions of x. So P1 is a linear function of x, P2 is a quadratic, and P3 is a cubic function of x. So we can write them explicitly. The second step is to estimate the autocorrelations from the data. Okay, so for example, AY1, autocorrelation of y, the first one, is just the average of the entries of y. We can just average over the measurement. The second order autocorrelation, AY2, is I take my measurement, I take a shifted copy of the measurement, and I take the product and average. And I can do the same for the third order autocorrelation. And by the law of large numbers, we know that if we have enough data, then these empirical autocorrelations are more or less equal to the expected autocorrelations. The third step is to try to solve this system. In our case, this is a system of polynomial equations, where the solution is going to be my estimator. Okay, so this is autocorrelation analysis. It's a special case of the method of moments that Joe is going to mention in the next talk.
Why do you say solution? You can calculate the right-hand sides, right?
The what? Sorry?
You don't have to solve, so you can calculate that straight away.
Usually you don't. You can just calculate it. So you have functions of x. These are like equations of x, and this is what you compute from the data, and you want to find x which is consistent with these guys. Sometimes it's quite easy, but usually it's actually very difficult.
The third line, okay, yeah.
Yeah, so it might be easy, but usually it's quite difficult actually.
Solving polynomial equations is not easy.
He's meant the equation is the second.
Yeah, but
equality, sort of.
Yeah, but the first.
Yes, so this method, it has some very appealing properties. So first of all, it's very simple. It requires only one pass over data. We just need to go through the measurement only once, in contrast to other techniques that you go through the measurement over and over and over again. Usually it's a consistent estimator because we can relate the data directly to the parameters of interest, but it's not statistically efficient, like maximum likelihood, for example. So that's a downside. So let's see how we can apply autocorrelation analysis to multi-target detection, to the simplified model. So I remind you, so we have, if we look, for example, at this model, we have a long measurement and we have multiple signal coordinates. We don't know where they are, and we want to estimate the signal. So in this case, if the signals are not densely packed, it can be shown that the autocorrelations of the measurement, here is AYQ, Q is the first, second, third, and so on, are equal to gamma times the autocorrelations of the signal, AX of Q, where gamma is just a density parameter. It's a number between 0 and 1. It's not very important for us. So this result, this relation, implies that we can relate the measurement, quantities of the measurement that we compute from the data, to the signal directly. So we don't need to know where the signal is. Okay, so we can relate the measurement to the signal without knowing where the signal occurrences are. And specifically, we can show that if you can compute the third order autocorrelation, AY3, then it determines the signal uniquely. So we can recover the signal from the data. And this is true in any SNR. 1 second, okay? And this is true in any SNR, and we don't need to detect the signal. So the SNR may be very low, so detection is impossible, but we can still recover the signal uniquely. And this is true if we can estimate the third order autocorrelation. So these are triple products. So overall, we need that n, the length of the measurement, which should be much greater than sigma to the 6. Sigma to the 6 because we take triple products. So the variance is sigma to the 6. We need the length of the measurement to be much larger than sigma to the 6. So again, this means that if we have enough data, in this sense, even if the SNR is very, very low and we cannot detect the signal occurrence, I have no idea where the signal appears in the data, I can still estimate the signal itself quite accurately. Okay.
So here you're assuming that your signal is the same. So my worry is now I have the marginalization over the post.
We'll be there.
So, okay.
5 minutes. Yeah. Very good question. Okay, so the point here is it's a simplified model of cryo. There is no rotations, but the main insight here is that we can determine the signal from the data directly, and we don't need to detect the signal occurrences, which sometimes we just can't do that if the SNR is too low. So let's see a numerical example. So this is part of our measurement. You can see 3 signal occurrences in 1 dimensional. These are the blue. I hope you can see that. Here and here. And the green is the measurement. So the SNR is low, the noise is much larger than the amplitude of the signal. So we took this measurement and we computed the first 3 autocorrelations and we tried to estimate the signal itself, again, without detection. And here you can see 3 recoveries in red, orange, and purple. So you can see that if we don't have enough data, in this case, in the red curve, we don't have enough data, we can't estimate the third order autocorrelation accurately, and therefore we cannot estimate the signal. So that's why we get quite this kind of estimation. But if we do have enough data, it's the same as SNR. So we still cannot detect the signal occurrences, but we have enough data, we can estimate the signal very accurately. This is the purple line. 1 second, okay? And in the right panel, you see the y-axis is the error, and the x-axis is the length of the data. It's the number of signal occurrences. And you can see that the error decreases like 1 over square root of the number of signal occurrences, which is what we expect from a good estimator. So that's a good rate for us.
Yeah, so what do you mean by data? Do you need 10 to the 7th micrograms? So for what do you mean by data? Do you need 10 to the 7th micrograms?
So here it's a 1 decay. So we take longer and longer measurements. Okay? But in cryo-EM, it means like more and more micrograph. You can think about if I use like 10 micrographs, 100 micrographs, 1,000 micrographs, and so on.
Yeah, sure, but it's not if you have a longer micrograph, that already helps. You don't need, so you can sort of scale in both the size of the micrograph and the amount of micrographs. That both amounts to better.
Yeah, but again, the point is that if you want to do particle picking and the SNR is low, it doesn't matter how much data you have. You can never detect the particle projections. So you cannot, if you go in the standard current computational pipeline, it's just going to fail. It doesn't matter how much data you collect. And here in this method, the fact that you collect more data actually helps you, which is what we expect from a good estimator. And this is exactly the rate that you should expect from a good estimator, right? This is by the law of large numbers.
I have a quick question.
Yeah.
So the effective like pixel size would be fixed here? As you have a longer micrograph,
Yeah, so here
sort of
this
have
is
more
this is a discrete
forces.
example. So we started here with like 10 to the 4, and here we have 10 to the 7. That's the number of signal occurrences. Yeah, there is no. It's completely discrete in this case.
The
Discrete
sample
part.
rate is the same always.
Yeah, you can think about it like this. Yeah.
Can you comment about like like more micrograph in the sense of like longer signal versus more particles, and so kind of dense, kind of more concentrated?
Yeah, so that's a good question. So we have this parameter gamma, which basically quantifies the density. So in some sense, higher density, you have more signal, you're in better position. There is a caveat that I don't really mention here because I don't want to go into the technical details, but we do assume that the signal is not very close to each other. So it's another restriction, but we know how to overcome it. Just the model becomes a bit more nasty, but we know how to do that. Okay, so other way around. Yeah, so now let's see how we can take it to cryo-EM. Okay, so in cryo we have a micrograph to the 2D image, and we want to estimate the 3D volume. And in this, again, I'm not diving into the technical details, but we assume that the structure has some band limit, which is L, and therefore we want to estimate n cube parameters. This is the number of parameters that we want to estimate. So the way we do that, so we scan the micrograph as like a sliding window, and each window we compute for each window the autocorrelation is an average of all the windows. So for example, the first order autocorrelation of each window will be just the average. So basically this is just averaging over the micrograph. It's not very informative. The second order autocorrelation is, for a specific window, we take the center point and another point. We take this double product, and then we average over all windows. The third order autocorrelation will be the product of the center point with 2 additional points. This is like a triple product, and again, we average over all windows. This is how we compute the autocorrelations. And then you can show the following relations. So what it means, so on the left-hand side, this is what we compute from the data. These are the autocorrelations of the micrograph. Okay, so that's the data part. On the right-hand side, this is the relation to the volume. So here x is the volume. P omega of x is the projection of the volume from viewing direction omega. Omega is of SO3. So this is an image. P omega of x, this is a 2D image. So A1 of P omega of x is just the first autocorrelation of the projection image, and then we average over all viewing directions. So in the limit where we have infinitely many data, so the autocorrelation of the first autocorrelation of the micrograph is equal to the average over the autocorrelations of the projections times gamma, which is again the density parameter. So the same holds for the second order autocorrelation. So this is the second order autocorrelation of the data. And this is equal to gamma times, we compute the second order autocorrelation of each projection, A2 of P omega of x, and then we average over all viewing directions. And the same for the third order autocorrelation.
I mean, can you just go back to your previous slide for a second?
Yeah.
Okay, so you do this window of size L by L, so the idea is there should be, if you're lucky, there's a particle in that window? Is that?
Doesn't matter.
But, I mean, that's why you pick that.
No, you go through everything. So in some windows will be pure noise,
Right.
like nothing. Some windows will have like a full particle, but some of them will have different parts of the particle because we scan through everything.
But the window is particle sized.
Yeah.
That's,
yeah,
so
yeah.
you wouldn't expect to find multiple particles in the window when you do it this way.
So that's.
I mean, you might find half of 2 particles, but not.
So here I assume they're separated. So each window contains at most 1 particle, but in principle you can extend it to account for if they're densely packed, and then some windows may have 2 particles. You can extend this framework, it's just a bit more nasty.
And I think another way to ask it, you assume that you know the particle size.
That's another question, but yes, we assume to know the particle size. Yes. Okay, so again, these are the autocorrelations we compute from the data, and these are functions of the volume, so are parameterized by the volume, and we have explicit expressions for this. Okay, they are not very nice, but we can compute them analytically. And the point again is that we relate quantities of the micrograph to the volume directly. We don't need to know where the projections are. And therefore, at least in principle, we can work in very low scenario where detection is impossible, and therefore, hopefully, small molecules are within reach for us. 1 second, okay? Okay, so that's what we get from the data. These are quantities of the volume. So here it seems like that this is like a 4-dimensional structure, but because of symmetries of the model, we actually have like n-cube equations, and want to estimate n-cube parameters of the volume, so we can try to find the volume that matches the empirical autocorrelations.
So I'm just wondering about the space of the averages, like those would be,
This one?
or the top one even, that would be like a n by n, and then there's this density,
What do you mean?
Yeah.
What average? Like this
the
one
average of the
or this one?
projection of A1 P omega x over omega.
So
just
these
a
are the
real
things that we can actually compute it. Like you compute it with a paper and a pen. But basically, this is like, I have a 3D structure. I parameterize it somehow. It's not very important for this talk. I compute the projection, again parameterized by the volume. So this is P omega of x, and then I can compute the autocorrelations of this projection. This is an image. I can compute the
And is that a
autocorrelations.
real number? Is that a real number? So the projection is like some vector, and then the
In our case, these are complex numbers, but it depends how you parameterize your volume. And then you need to know how to do this integration, because you need to integrate over SO3. So I can show you, like, it's on the paper, but basically this is like a very explicit expression of the parameters that describe the 3D structure.
but the left-hand side, the right-hand side, they're scalars.
These are not scalars.
Or tensors.
No, this is like a 4D array.
Okay.
So again, in practice, this is a 3D array because of symmetries.
Okay.
What do you assume about the noise?
So here we just assume wide Gaussian noise.
White noise.
But the most important part for this work about the noise, it's not actually that it's wide Gaussian, but that you can average it out using the law of large numbers. So it's a bit more general. Okay, so that's the data part, and this is the relation to the volume. So you can try to find the parameters that fit the empirical autocorrelation that you compute from the data. And we tried actually many things, but basically tried, for example, to minimize a least squares objective. It's non-convex, but you can try different optimization technique. And again, I didn't write down all the small details, but they all appear in the paper. And perhaps the downside, I'll show you a numerical example in the next slide. But before that, the main problem that we encountered is that this mapping, we have a mapping between the volume and its autocorrelations, it seems to be unconditioned. This means that different volumes may provide very similar autocorrelations, which is very problematic for us. Okay, so that's the main problem that we're facing currently. So this is one numerical example. So this is the TRPV1 protein. This is the structure, the high resolution structure in purple. We downsample and smooth it. We take a smooth version. So in the cyan, you can see, this is still the ground truth, but after downsampling and smoothing, and this is what we recovered. And that's basically more or less the best we can do nowadays. So we have problems with the numerics that this mapping seems to be unconditioned. This is the main problem we are facing. Yeah.
So if you start from a good guess, do you get to the right solution?
It should be very good. No,
It's a cryo-EM problem in general.
No, but here it's way worse than, for example, in expectation maximization. It's a big problem for us. Yeah, it's much worse than expectation maximization. Yeah. So the question is how to solve it. That's where we are currently with this project, and I think that there might be different solutions, but I think that the main issues that we need to solve is to find a very good prior that somehow differentiate between the relevant structures. And this prior might be either analytical prior or, I don't know, biologically oriented prior, some statistical properties of proteins, or perhaps just data-driven prior. If we have enough structures that we already resolved, we can somehow understand what is a typical protein, typical structure, and perhaps we can plug it into the machinery to allow us to differentiate it. So that's I think, the main. This is the main problem, and I think this is a solution, although we didn't solve it yet. There are, again, here the model is a bit simplified. So, for example, we didn't consider CTF, and we assume that the particles are quite far apart. I don't think these are big problems. I think these are things that can be easily handled, and we know how to do that. I think the first one is the unconditioning is the issue. not considering a more intricate statistical model. I also want to mention that the group of Amit Zinger, they used a very similar technique to a problem of random conical tilt, and they got very good results, very good numerical results, but this is a bit an easier problem because they need to average only over SO2 and not over SO3. And something else that just occurred to me while I'm preparing the slides is that perhaps even with the current results, perhaps it might be useful. So for example, if you have we never done that, this is just a thought. So for example, you have a data set with very low SNR, it's very hard to perform particle picking because, for example, you don't have very good templates or whatever. Then perhaps you can run this algorithm on your data set, get a very rough estimate of the structure, some very low estimate of the structure, and use it to generate the templates in order to run template matching. So this is something that perhaps can be done. Again, I've never done that, but this might be, perhaps it might be useful. And the last point is that perhaps we should consider different techniques that will allow us to get better results. And that's the next part of the talk.
I have two questions. So here you're assuming that your orientations are uniform.
Yep.
So how would you tackle that averaging if
it's not uniform? I can tell you in theory, but we're not there yet. Basically, so what you would do, like in one sentence, is you're going to parameterize your distribution, and then you can compute analytically the autocorrelations with respect to these parameters as well. And then in your optimization problem, try to match both the volume and the distribution simultaneously. This is probably, again, if it will work in this case, that's something that we should do, but we are not there yet.
And that could also be generalized for conformational.
Yes, in principle, you can also think about heterogeneity and so on, but we are not, like, we don't really know how to solve the homogeneous case, so, yeah. Yeah.
So I have a different problem for you, actually. Let's take the same
Wait
methodology.
a second.
This methodology is good, might be applied in a different place, might be, that's why I'm suggesting. So when we do molecular dynamics simulations, we have a protein in a water box. And we often ask the question, what is the collective motion or the slow motion of the protein? There's a lot of noise, again, the signal to noise ratio. You can still see like the signal to noise ratio of the protein, somewhat you can visualize that, eyeball it, there's so many other dimensionality reduction methodologies to do that. But there are modes of the water also that is around it, which is like the small structure, the equivalent to a small structure there. And it's very difficult to see if there is any pattern in water that is coming up. The problem there is, if you get into the kind of analysis that you're showing, the averages of the autocorrelations, the autocorrelations are actually analytically defined there. Something called the Green-Scubo functions. It's essentially a friction-dominated Ranchenmann function. So I have two questions essentially. So first of all, can you take this entire setup and move it to a place where the correlation analysis is analytically established, and see if you can compute these averages and if they make sense? Often it's very difficult to compute those averages in other settings, which might be.
I really don't know the problem. So basically, like autocorrelation analysis and the method of moment, these are like very classical parameter estimation techniques. It appears in books from the beginning of the 20th century. As I don't know, I understand. It's a good question. I'll be happy to discuss or to see the papers or whatever, but I don't know, I don't know. Hopefully.
Because when you compute your averages, what are the kind of problems? Do they converge? Like what kind
So currently the main problem that we are facing, so you might think about different problems, but the main problem is that we need to solve a polynomial system of equations. In this case, a cubic system, and solving polynomial equations, specific in high dimensions, usually it's very difficult. It's very, very difficult. It's known problem in algebraic geometry, or like mathematicians know that. It's very difficult. So I think this is the problem.
We have a question from Chris. Yes. I find this very interesting, but two questions for you. One is what I asked you yesterday, robustness to not having a particle in the box, actually. So if, let's say, 90% of your particles are not particles, it's not a problem.
No, it's part of the system, actually. So suppose you have a micrograph and just scan through everything. You see some parts, some windows is only noise, but all the different parts. You scan through everything. So that's not a problem.
That's what I thought, but you just have to have the limit of enough particles, essentially. And then the second one is, have you made any assumptions about smoothness, and could that be a prior?
Yes, so I didn't describe how we model the structure, but actually I'm going to show it in a few slides in the context of the second method that I want to show. But yes, we expand the structure in something like Fourier series. You have some band limit, and the band limit determines the smoothness of the structure. So we do, yeah.
So I guess one radical thought that you're presenting here is that there shouldn't be a size limit.
The what?
There shouldn't be a size limit or a molecular weight limit. And I think I agree with you. I just wanted to check whether I think about this correctly. As long as you have a likelihood measure that tells you for a given structure how likely it is, you can go to any size you want. Because you can basically go through your voxels and try all of them at different values and evaluate them until you get the highest likelihood. Of course, computationally that's
not even computationally,
but
statistically.
is this kind of what you're trying to?
No.
No?
So the point, I think that the main point, and I really want to go to the second part because I want to show it, because the results of the second part are much better. So. But just to give you an answer. So the point is, what do you actually trying to estimate? That's the point. So in cryo-EM, we usually, because it's a good idea, but if you can, we're trying to, first of all, detect the particles, and if we can actually to determine the rotations, which is a great idea if you can do that. But the point is, if the SNR is low, like if the noise is high, you can do it by any method. It's not a computational problem, it's a statistical problem. And you can actually prove that it is impossible. However, if you marginalize over these parameters, and you only try to estimate a fixed number of parameters, then again, you're in a good position. And as you get more, and you collect more and more data, for example, maximum likelihood is going to be consistent. So we know this is like classical estimation theory. So it's not about how you do that. It's not about the algorithm. It's about what you can do and what you cannot do statistically.
Let's continue.
Yeah, right. Okay, so now I want to show you another approach, slightly different or completely different. And this is what we call approximate expectation maximization. So I just want to remind you what is expectation maximization. You all know that because this is a very basic tool in cryo-EM. So EM, expectation maximization, is a general algorithm that we use in order to find the local maximum of a likelihood function, or more generally of posterior distribution if we have a prior, with nuisance variables for statistical models that contain nuisance variables, like cryo-EM. It's a very general framework. I want to focus on specific family of models of this form, where we have a signal x. In cryo-EM, x is going to be the 3D structure, and each observation x is actually defined by a random linear operator. Okay, so N theta is a random linear operator where theta parameterizes. Theta is a random variable that belongs to some set of possibilities, capital theta. So for example, in cryo, x is going to be the structure, and N theta is going to be the rotations and translations, and capital theta will be all the possible rotations and translations that you consider in the algorithm. Okay, so the goal is to estimate x from n observations. I use boldface y for the stack of images. And when we treat the thetas as the nuisance variables, again, for example, in cryo, these are the rotation translations, we treat them as nuisance variables. So we don't know them, but the goal of the estimation task is not estimating them. And you can write down the likelihood function. That's what we usually do. And here, again, the specific expression is less important. The important point to note here is that we marginalize, we sum over the thetas. So we sum over the nuisance variables. So the likelihood function is just a function of x, of the parameters of interest. So we marginalize over the nuisance parameters, and we only want to estimate x. Okay, so that's the likelihood function that we want to maximize. So what do we do in EM? So basically, we write a function. Usually, we use k to denote it. I don't know why. I think it's from the original paper, 77. So q is a function of x the parameter given xt. Xt is the current estimate of x. And we write down the so-called complete likelihood, which is a likelihood function where we assume that we know the nuisance variables, which is usually a simple function. And then we take the expectation with respect to the nuisance variables given the current estimate of the structure. And when you do that for the models that we consider here, you get a very nice expression. Well, here you just have like R to distance, and you have these weights because of the expectations, and the weights are just like Gaussian weights, which is the probability that theta is equal to theta r given yi and the current estimate of the signal. And then in EM, we run two steps iteratively. We have the E step, where we compute the weights, these W's, these guys, given xt, and then we try to maximize q. In our case, basically we just need to solve a linear system of equations for this case, and then we run these two steps until we stop at some point, say converge to something. So EM, as far as I know, it was first introduced to the cryo community by Fred Thigworth in '98, but currently it's a very popular framework. You use it for refinement, like 3D reconstruction, but also for other steps like 3D classification and 2D classification. And the strategy currently is to first locate and extract the particle projections. Like first you want to run particle picking. You get a stack of images, and then you run the EM on this stack of images where the space of possibilities, this capital theta, is a 3D rotations, and we usually allow small 2D translations. So that's the standard algorithm. That's more or less the standard framework in the field. However, again, if the molecule is very small, the SNR is very low, we cannot perform particle picking. Particle picking is just going to fail, and therefore this entire paradigm just fails. And the question is whether we can, rather than do particle picking and then run EM, can we run EM on the micrograph itself directly? Okay, so that's the question that we want to consider. Yeah.
There is one subtle point here. It's not just the particle picking that creates the failure in the algorithm. You can pick particles that you cannot align and determine the 3D structure of currently with the...
Align, you mean like find the rotations?
I mean, you can see that there's a dot in the micrograph and you know that's a particle, but you feed it into the programs, even with a very large data set, and you never get anything useful out. So it's failing before it's reaching this limit that I think you're talking about.
So basically the limit is, like the fundamental limit, again, from statistical perspective, is the limit of estimating all the pose parameters, like the detections and the orientations, where the main issue is that the number of parameters increases with the number of observations. And if that scenario is too low, you can't do that. And we try, that's what I want to show you now, how we can use a modification of EM to marginalize over everything, the rotations and translations. But I agree that the actual picture is a bit more complicated than my a bit simplified model here. I agree about that. Okay, so to understand that, let's remind ourselves the multi-target detection, the simplified model. So we have a 1D measurement, and there are multiple signal cornices. And if the SNR is low, we cannot detect the locations of the signal cornices, and we want to estimate the signal from this kind of data. So basically, this is you can write this model in a very explicit statistical model, and you can write the likelihood function. You can try to run an EM directly for this model. It is possible. You need to be a bit careful, but you can do that. The problem is that if you do that, suppose you have like k signal cornices, like 3. In the E step, you need to assign probabilities to all different configurations. In this case, it's going to be like n choose k configuration in each E step, and which is a huge number. So we cannot really. It's completely intractable. Okay, so even if you in principle can run EM, it's completely intractable in reasonable data size. So we need to do something else. And this is exactly what we call the approximate EM. So I want to explain it. First of all, I'll try to explain, show you the formulation, and then I'll try to illustrate it to explain the point. So what we do is very natural. We take the measurement, and we split it into n over n non-overlapping patches. So we just split it into different patches, and we're going to assume that they're independent. This is the approximation. This is not true in practice, but this is the approximation that we take. So let's see this. So that's my measurement, 100 entries, and I just split it into 10 different patches. You see the vertical break lines. So you can see that some patches, like this one or this one, they have no signal. So this, if we have noise, if the measurement is noisy, then these are going to be like pure noise patches. We have other patches, like this one, that they catch like a full signal. So this patch has a full signal, in general, signal plus noise. But we have other patches which contain like different parts of the signal. So we want to find a model for each patch that somehow describes all the different possibilities. Okay, so this is how we model each patch. So again, I try to explain and then I try to illustrate it so it will be clear, I hope. So we want to maximize the approximate likelihood function. 5 minutes? Oh, so it's going to be very fast. No, I can take 5 more minutes. There's many questions. I can take 5 more.
Yes, so we are already over time in terms of 50 minutes. So because I asked you so many questions,
okay. Okay, so I'll try to do it very quickly, and I'll be happy to talk with you afterwards to explain it that you may understand.
Yeah. 5 minutes on the clock.
Give me the 5 minutes. Okay, so we want to maximize this likelihood function, which again, it assumes that the patches are independent. And this is the model that we consider. So basically what it means is that we take the signal of x, we zero pad it, we shift it circularly over the zero padded signal, and then we crop it again. So let me illustrate that. So we have this. So for example, this is my signal of 100 entries. This is x. Zx is going to be the signal padded with 100 entries. So this is of length 200. Then, for example, here I shift by 25 entries. So for example, I get this one. And then I crop the first 100 entries, and I guess this part. So this is an example how I can use this model, and I can add noise. Example how I can use a patch, how I can get a patch where it contains only the left part of the signal. So I can do the same with 125 entries, for example. So again, I do it a bit quickly, but basically you get only the right part. So you can get different parts of the signal. You can do the same to get the full signal if you shift it by 0 entries. And if you shift it exactly by 100 entries, you just get pure noise. So again, I know it's a bit quick, but basically the idea is that you can use this model to describe all the different options of a patch, like full signal, no signal, or different parts of the signal. And never mind. Okay. And then we can apply EM to this model. Now a very, very explicit model. And this is just a linear operator parameterized by theta. So it's exactly the same scheme that I showed you before. We can just run standard EM for this model. So now we can take the same ideas to cryo-EM. So now we assume that micrograph is just a combination of projection images. So X is my 3D structure. P omega of X is the 2D projection from viewing direction omega, and it is shifted by some Li. This is the center of the projection. So, and noise. So this is my micrograph. We model the 3D structure. We can write down a projection. I skip about the details. But the point is that eventually we can write a very clean model for patches. So we take the micrograph, we split it into patches, and I can describe each patch using this formula where, again, X is my 3D structure. P omega of X is the projection from viewing direction omega. I zero pad it like in each direction because now it's 2D. I shift it by some circular shift in 2D, and I crop it again to the same size and add noise. So this is the extension of this 1D EM to 2D. And here we have a 5-dimensional nuisance variables. So these are 3D, these are 3D rotations and 2D translations. So we need to average out 5D space. And again, all the technical details appear in a paper that we didn't publish yet, but it's ongoing work. I want to show you a few numerical experiments, and that's going to be the end of the talk. So currently we work with very small structures of size 11 times 11 times 11, and we expand them, never mind. The SNR of the data is 3.5 it's not as low as we want. So currently we're trying to push the SNR much lower because that's the goal. We want to recover structure in extremely low SNR. So currently the SNR is something like this in the results that I'm going to show you. And the rest of the detail. Okay, so let me just show you some results. So again, so we took the data, we generated the micrographs as I tried to explain, and we covered the 3D structure directly from the micrograph without particle picking. So here we did it with the shape log phantom. And this is the original structure with our expansion. This is what we could recover. This is for the TRPV1. This is the original smooth structure, and this is our recovery. For this, the ATS ribosome, and for the BPTI mutant. Okay, so again, that's the structure, and that's what we could recover directly from the micrograph without particle picking. So that's where we are at the moment. This is the next slide. So we discussed two methods to recover structures directly from the micrograph, and we hope, or that's what we're hoping to get, that it will pave the way to recovering small structures using cryo-EM, which is something that we do not do today. The autocorrelation analysis is computationally very efficient, but currently we can get only low-resolution estimates. And I think that the solution should be designing meaningful or good priors for this problem, which is currently a missing ingredient in our algorithm. The approximate expectation maximization provides much better recoveries. We get quite high-resolution recoveries, but currently the SNR is not as low as we want. So first of all, we need to accelerate it. We need to accelerate the algorithm to work on larger data sets and to sample, for example, SO3 more densely. And again, designing priors. We like to do theoretical analysis, so we want to understand sample complexity, like what's possible, how much data I have to acquire in order to recover structures for a given SNR, and also the analysis of the EM iterations. And the last point is perhaps we can use like I showed you two methods, but basically perhaps we can use other techniques. So for example, there is the paper of the cryogun, where you basically use the GAN network. So at least in principle, you can use the cryogun to try to solve this, to try to maximize this approximate expectation maximization. I think it should be possible. And I think that perhaps we can actually do it with dynamic programming, which would be very nice because it's going to be, if it would work, it's going to be extremely fast. But I'm not completely sure about it yet. And that's it. Thank you very much.